Howdy there, folks. I'm Jeff Sengpeel. I've spent a few years talking with many folks from all sorts of parts of the industry on what AI could do for them and for their workflows. So, if we haven't had an occasion to chat, let me walk you through some of these fundamental artificial intelligence terms to give you the foundational definitions for concepts in AI in this video. I'll help you start on a comprehensive understanding of these terms. First off, artificial intelligence. At its core, artificial intelligence, or AI, is technology that simply aims to replicate human-like intelligence and decision-making. Think of AI as giving computers the ability to perform those tasks that have always required human thinking up to this point. Just as humans can recognize faces, understand speech, make certain decisions, and learn from their experiences, AI systems are designed to do the same, but through computational means rather than a biological process. Helpful way to understand AI is to compare how we humans learn and think. When we recognize a dog, we process the visual information that we see, compare it to our previous knowledge of dogs, make a quick decision. AI does something similar, but using mathematical and language models coupled with algorithms instead of neurons and synapses. The key difference is that while humans naturally learn and adapt, AI systems need to be carefully designed and trained to perform specific types of intelligence. Can I pet that dog? All right, algorithms. An algorithm is, at its core, a detailed recipe for solving a particular problem. Just like a recipe tells you exactly what ingredients to use and what steps to follow to get a cake, an algorithm provides a computer system with precise instructions for completing a task. However, an algorithm in AI is a lot more complex than a simple step-by-step instructions from Betty Crocker. Consider how you would teach someone to play chess. You might start with the basic rules, the basic movements of the pieces, and then you move on to strategies and patterns. AI algorithms work similarly, but with mathematical precision. They take the input, current state of the chess game, process it through a series of defined steps, and produce an output, telling you what its next best move is. Modern AI algorithms often handle incredibly complex tasks. For example, when you use a navigation app, multiple algorithms are going to work together to, first of all, figure out, with the map data, understand all these road networks. 2, calculate potential routes between you and your destination. 3, analyze the real-time traffic data. 4, determine the optimal path based upon a whole bunch of various factors. And then 5, continuously update recommendations as conditions change, or if you're using Waze, you're just going to turn left now. So let's get to time-based metadata. Time-based metadata adds an important temporal dimension to information about digital content. Imagine you're watching a long documentary film, and someone says, "This thing happens in the film." Time-based metadata is going to tell you exactly at what time code that specific topic is discussed, or when specific people appear on the screen, or when important quotes pop up. This temporal organization of information makes it possible to quickly find and access specific moments in media content instead of just pointing to the overall clip. Clip-based metadata is very difficult when you have longer clips. Pointing to 2 hours of footage when you need 3 seconds doesn't make much sense. This concept becomes extremely powerful in modern creative tools and asset management applications. For instance, if you're watching a streaming service and it shows you the preview thumbnails as you scroll through on the timeline, that's time-based metadata there at work for you. It's also what allows editorial platforms to provide chapters, automatically generate highlights, or let you skip to specific scenes. Application Programming Interface. Quite a mouthful. We just call it API. You've heard of that. An API just serves as a bridge between different software systems, enabling them to communicate and share data. An API, just think of it like a waiter in a restaurant. The waiter, the API, takes your order or the request, delivers it to the kitchen, which is the server or database, and then brings back your food as the response. You don't need to know how that kitchen works in order to get your meal, just as applications don't need to understand each other's internal complexities to exchange information through an API. In practice, APIs enable countless modern technologies. When you use a weather app, it's likely using an API to fetch the weather data from a meteorological service for your location. When you pay for something online, payment APIs Handle the secure transaction between your bank and the merchant. Creative tool sets use APIs to talk to each other, allowing integration of these different tool sets into your interface. Machine learning. Machine learning represents a fundamental shift in how we program computers. Instead of writing all of these detailed, explicit rules for every single possible situation, and missing a whole bunch, we create systems that can look at patterns from data and work to improve their performance over time. This mirrors how humans learn from experience rather than following rigid instructions. The way to look at this is very simple. First of all, the system receives training data. These are clear examples of what it should learn, like a picture of a person. It then analyzes this data to identify patterns and relationships in it. It will then create a model based upon those patterns it's now knowing. It then can use these models to make predictions, go through other material, search, and or make decisions about new situations. Deep learning. Deep learning represents a more sophisticated approach to machine learning, inspired by how the human brain processes information. Imagine how you recognize a friend's face. Your brain processes visual information through multiple layers of neurons, each handling increasingly complex features. First, you might notice basic shapes and edges. That's a person. Then these combine into features like eyes and a nose. That might be Joe. And finally recognize the whole face as belonging to your friend. Yeah, that is Joe. Deep learning systems work similarly, using artificial neural networks with multiple layers. That's why they call it deep. Each individual layer processing information and passing its findings on up to the next layer. It's going to create increasingly sophisticated understanding through this process. The layered approach allows deep learning systems to handle incredibly complex tasks like understanding natural language and all its nuances, recognizing objects in images with high accuracy, creating realistic artwork or music, translating between languages while maintaining context and meaning. Generative AI. It's a huge buzzword out there. Generative AI represents a remarkable advancement in artificial intelligence, systems that can create new content rather than just analyzing existing data. Think of it like the difference between an art critic who can see and analyze paintings and an artist who can create whole new ones. Generative AI produces various types of content, including text, images, music, and even computer code. Process works by training the system on massive amounts of existing content, which is why everyone's interested in seeing more and more content. It allows them to understand patterns and structures and styles. For instance, a text-generating AI learns not just vocabulary and grammar, but also writing styles, narrative structures, and conceptual relationships. When you ask it to create something new, it draws upon this learned understanding to generate original content that follows similar but not exact patterns. Hallucination. In the context of AI, hallucination refers to when an AI system generates or presents false information with apparent confidence. This is really different from simple errors. It's more like when AI makes things up. They sound plausible, they're just not true. Understanding hallucination is crucial because it represents one of the key challenges in current AI systems. Also, hallucination becomes very interesting if you are asking AI to create a concept and it hallucinates something that you wouldn't even thought of. Think of it like a student. When faced with a question they don't fully understand, they create a plausible sounding answer instead of admitting their uncertainty. AI systems can do this, but in very sophisticated ways. They generate responses that seem detailed and very authoritative, but contain fictional or completely inaccurate information. Image recognition. Image recognition technology enables computers to understand and interpret visual information from the world. We also, in the industry, call this computer vision. The process is far more complex than simply detecting pixels. It involves understanding objects, context, and relationships within images that are moving. The system must then break down an image into meaningful components and identify what these things represent. Process can have several steps. One, breaking the image down into basic visual elements, edges, shapes, colors. Then you identify specific features and patterns. Then you compare these patterns with learned examples. Then you take and make decisions about what this image actually does contain. And then, having done all that, you can understand the context and relationship between these objects. Sounds kind of familiar with what we already talked about. Large language models, LLMs. You've probably heard that term. An LLM represents a significant advancement in AI's ability to understand and generate human language. These systems are trained on enormous amounts of text data, billions of words from books, articles, websites, and other sources. Through this training, they develop a sophisticated understanding of language patterns, context, and meaning. Think of an LLM like a highly educated person who has read a vast library of books and can draw on all of this knowledge to understand and respond to questions, to generate text, or to solve language-related problems. The large in LLM refers not to just the amount of training data, but the complexity of the model itself. It often can contain billions or even trillions of parameters to help it process language. Natural language processing, or NLP. Natural language processing bridges the gap between human communication and computer understanding. It's what allows computers to understand, interpret, and respond to human language in its natural form, rather than requiring a precisely formatted command. NLP involves multiple language analysis. First of all, it has to understand individual words and their meanings. Then it has to recognize the grammar and sentence structure. Then it has to interpret context and nuance. We humans are all about nuance. And then it has to recognize sentiment and emotion. Sarcasm font, anyone? Then it needs to have an understanding of the broader meaning and implications of what is being said. Prompts. A prompt is much more than just simple input. It's the way we communicate our intentions and requirements to AI systems. Think of a prompt as having a conversation with someone who's incredibly knowledgeable but does still need precise instructions to understand exactly what you want. The art of creating effective prompts, what is often called prompt engineering, has become increasingly important as AI systems have grown more sophisticated. Creating effective prompts involves understanding several key elements: the specific capabilities of the AI system you want to use, how to structure that request for optimal results, the importance of context and explicit instructions, and how to refine and iterate based upon the responses you receive. You get something, you may not like what it does, and you may need to change your prompt to get what it is that you want out of the system. So if you have for example, you ask AI to write a story, simply saying, write a story. It's going to give you a very generic result. However, a well-crafted prompt might specify the genre, tone, length, key characters, and plot elements, leading to a much more targeted and useful output. If you tell the system, write me a story in the manner of Stephen King with 4 characters who are stuck in a snowstorm, that's a lot more than just simply telling me a story. Sentiment analysis. Sentiment analysis represents the intersection of emotional intelligence and computational power. Technology enables computers to understand the emotional tone and subjective opinions that are expressed in text, speech, or other forms of communication. Similar to how humans can detect whether someone's happy, angry, or sad based upon their words and their tone of voice. Okay, there's a lot of sophisticated steps in this. First of all, they have to break down the input, whether it's text, audio, or video, into components that are analyzable for it. Then it needs to, in that, identify words, phrases, or features that are going to carry emotional weight. It's then, third, going to need to understand the context and the nuance, including sarcasm and implied meaning. And then it's going to need to quantify the overall emotional tone based upon various scales. And then it's going to need to produce actionable insights from this analysis. So a real-world application of sentiment analysis, they're pretty widespread, from businesses analyzing customer feedback to social media platforms monitoring public opinion trends. For instance, a company might use sentiment analysis to automatically categorize customer service interactions as positive or negative, helping them identify areas needing improvement. How was your service today? Oh, it was just fine. How was your service today? Oh, it was just fine. That's sentiment analysis. Training data. Training data serves as the foundation for AI learning. It's essentially the educational material from which AI systems learn to perform their tasks. Just as humans learn from examples and experiences, AI systems learn from carefully curated sets of data that represent the types of problems they're going to need to solve. The quality and quantity of training data directly impacts an AI system's performance. Consider teaching someone to recognize different types of birds, but you only show them just a few pictures of common birds. Not going to prepare them to identify a rare species. Similarly, AI systems need comprehensive, diverse, and high quality training data to develop robust capabilities. Process of using training data involves this. You collect it, you gather the relevant, diverse examples, you prepare it, you clean it, and organize the data. Then you annotate it. You label the data with the correct answers or outcomes. Then you need validation. You test that data's ability and representativeness of what you're trying to accomplish. And then you need to implement. You take the data and use it to train your AI system. Unstructured data. Unstructured data represents one of the most challenging and interesting aspects of modern data processing. Unlike structured data, think a spreadsheet with clear rows and columns, unstructured data comes in forms that don't fit neatly into traditional databases. Things like emails, social media posts, video, photos, audio recordings. The challenge with unstructured data lies in its complexity and variety. Imagine trying to organize thousands of photographs. They do contain valuable information, but it's not immediately searchable or analyzable like a spreadsheet of numbers would be. Find for is much easier to accomplish than find me happy baby. This is where AI can become particularly valuable. Helps to make sense of all this seemingly chaotic information. Voice recognition. Voice recognition technology represents a remarkable achievement in human-computer interaction. It transforms spoken language into a format computers can understand and process. It enables natural verbal communication with machines. This technology has evolved from simple word recognition to understanding complex sentences, different accents, and even emotional tone. The process involves multiple sophisticated steps. Capturing the audio. You've got to record the sound waves of the speech. Signal processing, converting those sound waves into digital data. Phenome recognition, identifying the basic sound units of speech. Word recognition, combining those phonemes into recognized words. Context analysis, understanding the meaning of those words and how they mean in a sequence. And then response generation, producing appropriate outputs or actions. Modern voice recognitions can handle challenges like background noise filtering, multiple speaker differentiation, or what's known as diarization, accent and dialect variations, natural speech patterns and filters, and context-dependent interpretation. These technologies are going to continue to evolve, becoming more accurate and capable of handling increasingly complex linguistic challenges. If you'd like me to elaborate on any of these concepts or explore how they interact in real-world applications, please say something in the comments, and it's been great chatting with you.